Hello, folks. I wanted to talk a bit more about graded potentials. And so now that we've differentiated them from action potentials, I just want to talk about the different types of graded potentials that can be generated. And this will lead us into these next two concepts, the spatial and temporal summation, which we've already talked about a bit, and then presynaptic facilitation and presynaptic inhibition. So we're gonna tackle the different types of graded potentials that can be produced a little bit more explicitly, although we've talked about those as well. Um, so let's imagine that we've got different neurons here. So here's one neuron connecting to another. And what we're paying attention to here is the synapse, right, at this neuron. And we're going to pay attention to that to talk about different types of graded potentials. There are EPSPs, or excitatory postsynaptic potentials, and there are uh, IPSPs, inhibitory postsynaptic potentials. Okay, so we're going to use the same neurotransmitter in both cases here. We're going to use the neurotransmitter that we've seen before, acetylcholine, because it's important to recognize, and I want to highlight that a neurotransmitter doesn't dictate whether an excitatory postsynaptic potential or an inhibitory postsynaptic potential is created in the postsynaptic cell. What determines it is the type of channel that it binds to. That's what determines whether a graded potential is excitatory or inhibitory. Okay, so for excitatory postsynaptic potentials, what we're imagining here is this neuron here, which is the presynaptic neuron, is connected to this postsynaptic neuron, right? With this, of course, being the synapse in here. When an action potential arrives and charge rushes in, calcium ions rush in, synaptic vesicles fuse with the membrane, and let's imagine that these then trickle over here into the synaptic cleft and bind to some channels, right? So what type of channels could they bind to that would produce an excitatory postsynaptic potential? Hopefully this is an easy one for you. We've talked about it many times about the driving force on different ions that are inside and outside the cell. So definitely, and I'm just going to draw these as little boxes, right? Voltage gated? No, not voltage gated. Ligand gated. Sodium channels are one, right? So these are, of course, ligand gated. So they're definitely ligand gated channels. And the two types that would produce an excitatory postsynaptic potential in this postsynaptic cell would be sodium channels and calcium channels, right? Those are the two. And I'm drawing this here as, in fact, I won't. I was going to draw both of these, but of course, in what we think is that in most synapses, there's only one type of ligand-gated channel here, right? And only one type of neurotransmitter that's released by this presynaptic neuron, right? So we could have this be, sodium channels here, ligand-gated sodium channels. And of course, if those open, you get sodium rushing in, and you get that, what you'll get is a depolarization of the membrane. Or we could have calcium channels, right? So it could be that we have ligand-gated calcium channels. And of course, we know the driving force on calcium, or the diffusion gradient slash concentration gradient, is the same on calcium as it is on sodium. So if a neurotransmitter, released from this presynaptic cell were to bind to these calcium channels, then we would expect this influx of calcium, which is also going to produce a graded potential, and it's going to be an EPSP, an excitatory postsynaptic potential. So just a reminder of what that looks like, an excitatory postsynaptic potential. I'm going to just draw a really quick and simple thing here. We know we're measuring millivolts. This is time. This is in milliseconds, right? And if we're down here at -70 in our threshold, right? Remember, that's our resting potential. and our threshold is whatever it is, -55, right? An excitatory postsynaptic potential is going to do that. It's going to raise our potential. It's going to move it towards zero, towards the threshold, and then it's going to decay, right, over some amount of time. That's an excitatory postsynaptic potential. And it's going to be generated when either sodium or calcium channels open on this postsynaptic membrane. So now thinking about IPSPs, right, we just have to redraw this and we'll have a different set of also ligand gated channels. So in this case, for an IPSP, we've got the same neurotransmitter, right? We've got our acetylcholine neurotransmitter being released from this presynaptic neuron, diffusing over to the plasma membrane of this postsynaptic neuron, and we have it binding to a couple different types of channels, right? It could bind to a couple different types of channels. Could bind to ligand-gated potassium channels, right? And of course, if it did, what would happen? Well, remember, the equilibrium potential for potassium is something like, it's about -85 millivolts, right? That's what, if the transmembrane potential of this cell were -85 millivolts, then there would be no net diffusion of potassium anymore. There would be an equal number of ions moving into the cell as there would be out of the cell. But of course it's not, because resting potential is -70. So there is a weak driving force on potassium to leave the cell. And so if this neurotransmitter were to bind to potassium, we would get, there we go, potassium leaving the cell, right? And that would, of course, be the equivalent of making the internal portion of the cell more negative, right? Okay, so potassium, these again are, let's see, I should probably do it in this, ligand-gated channels that are responsible for opening and allowing the diffusion of charge. But in this case, it can either be potassium channels or the other one, right, can be chloride channels. And I'll show you that one in a minute. And so remember that the chloride, the diffusion gradient is also out of the cell. And so chloride, is at very high concentration here and very low concentration there. So we can imagine what would happen if chloride bound to this. Right. We have our chloride channels here instead. And again, these are ligand gated chloride channels. And if acetylcholine were to bind to those and cause those to open, you would expect chloride to go along its concentration gradient, which would be, oh, geez, sorry. I just realized I made a horrible error in showing you the diffusion gradient of chloride. So let me fix that. Chloride is at much higher concentration outside of the cell than it is inside the cell. Right, so chloride is much higher concentration here than it is here. And so with the opening of these channels, you would get an influx of chloride, right? An influx of negatively charged particles, making this cell more negative, right? And so what you would have if we were to, graph this, let me just give us a little more space here. Okay, so if we were to graph this on a axes, like our simple axes over there, with our time and our millivolts, right? What we would expect when either the positive charge left the cell, or in the case of chloride, when a negative charge enters the cell, we would be here at resting, and we would expect a hyperpolarization, right? Certainly, that's clear when chloride enters, but also if positive charge were to leave, making this effectively more electronegative on the inside, we would expect a hyperpolarization that eventually goes back to resting. So those are the differences between types of graded potentials. Just quickly to summarize, right? These are graded potentials. They're of two types. They're excitatory postsynaptic potentials and they're inhibitory postsynaptic potentials. Whether a cell produces an excitatory or an inhibitory potential depends only on the type of gated channel that's in the plasma membrane, not on the neurotransmitter that's been released by the presynaptic neuron. Because whichever channels open, that's the charge that's going to be flowing through, and charge is only able to flow through channels down its concentration gradient. In the case of excitatory postsynaptic potentials, that could be either ligand-gated sodium channels or calcium channels, since the driving force on those positive ions is for them to enter the cell and therefore depolarize the cell and make the potential closer or to the outside of the cell, right? Or in the case of an IPSP, right, an excitatory postsynaptic potential, that would be if a neurotransmitter bound to either potassium channels or chloride channels. And in the case of potassium channels, that positive charge would leave, making this effectively more electronegative here and driving the cell further away from its threshold potential, which I neglected to draw, threshold and resting. Or it could be chloride channels that the neurotransmitter bound to, in which case chloride would flood into the cell, making it much more electronegative in here than it is outside, and also hyperpolarizing the cell, drawing it further from threshold, further from zero. Okay, this is going to allow us to think now more about facilitation and presynaptic facilitation and presynaptic inhibition, and also about spatial and temporal summation. Please let me know if you have any questions. I'll see you in a future video.